All right, the fundamental theorem of calculus part 2. So part 1 says that the derivative of the antiderivative just cancel out. You get back what you started with. In a sense, it tells you that integrals and derivatives are inverse operations. Second part, fundamental theorem of calculus part 2, tells you how we actually evaluate definite integrals. So we had an entire set of videos on the definite integral, and we had a bunch of things that looked like this, and we did them all geometrically. Like we would draw pictures and go, that's a triangle, that's a circle, that's a rectangle. Let's add up these areas. That's what this object here is. It's the area under little f from A to B. The second fundamental theorem of calculus says another way to do this is find any antiderivative of this guy and evaluate him at the endpoints and just subtract the two answers. And you can actually use the second fundamental. I've always wondered this. Like maybe I'll give extra credit for the first person that can send me an email and let me know. I've always wondered why we make this part 2 and the other one part 1, because you can use part 2 to prove part 1. Like I've always felt like this one should come first. And I have seen that in books. I've seen some books that call this part 1 and the other one part 2, but that's rare. This is more standard. Okay, so this tells us how to actually evaluate definite integrals. Remember, a definite integral is just a number. Our goal here is just to get a number. And we're finding the area under a curve. So like here, let's draw this guy out. I've got t squared minus 4. I know what that guy's graph is going to look like. The intercepts are at -2, 0, and 2, 0. He shifted down 4. Like we know what this guy looks like. What I'm looking for is this area. And I can see from the picture, I'm going to get a negative answer because we're down here. The fundamental theorem of calculus part 2 says to do this, find any antiderivative of your integrand and then plug in the endpoints. So the definite integral from -2 to 2 of t squared minus 4 dt. First off, remember we're allowed to integrate one term at a time. The integral is a linear operator. Constants get pulled out. We can distribute over sums and differences. So we're just going to integrate one term at a time. The antiderivative of t squared is t cubed over 3. Minus the antiderivative of 4 is 4t. Remember, we're doing antiderivatives, not derivatives. The derivative of 4 would be 0. The antiderivative would be 4t. Evaluated from -2 to 2. Now you might be thinking, wait a minute, what about, you goofed, Professor Perty, you forgot the plus c. No, I didn't. The plus c doesn't matter. Sure, you could put the plus c in, but then when you subtract top minus bottom, it's going to cancel out anyways. We don't put in the plus c when we're doing definite integrals. Okay, now this notation here, see what I've written? This means these are x or t values. That's my variable of integration. I'm going to plug in this and plug in that. Plug in the top for all of your t's, minus, and then in parentheses, plug in the bottom. We're going to do a bunch of examples. It's always top minus bottom. All right, what do we get here? I get 8/3 minus 8 minus, I'm going to keep this minus for a second. That will be -8/3 plus 8. Because a negative times a negative. And I've still got this negative outside there. So that will be 8/3 minus 8. Now I have to distribute. Here's where mistakes happen. You got to distribute that negative. Plus 8/3 minus 8. So now let's add these fractions. I get 16/3 minus 16, which we can go ahead and simplify. Let's see, that would be 48/3. So I think we get negative 32/3, because this would be 16/3 minus 48/3. So we did get a negative number, which we expected. Okay, let's do this one. This definite integral. Remember, a definite integral, your answer is just a number. All right, first, we don't know how to integrate anything that looks like this. We do not, there's no such thing as a quotient rule for integrals. We have, the only rule we know really is power rule, powers of x. So we want to write this using a bunch of powers of x. You are always allowed to split up numerators. If you have a sum or a difference on top, you're allowed to split that up as a bunch of different fractions. That's just how fractions work. So I can split that numerator up and write that as x over junk minus 1 over junk. Okay, now let's think about powers of x. That's x to the 1/2 How do we divide like bases? We subtract the exponents. So 1 minus 1/2, this is just algebra. I haven't done any calculus yet. No calculus has happened yet. 1 minus 1/2 would be positive 1/2. This guy would be better to write as x to the negative 1/2 because he was in a denominator. Don't forget your dx. You're never in your life going to write this symbol without having some kind of differential here. And that, like these parentheses are implied, this applies to the entire thing. All right, now let's do the antiderivative. Antiderivative, we're using power rule here. We're going to raise that exponent up by 1, x to the 3/2, and divide by the new exponent. So 1/2 plus 1 is 3/2 dividing by the new exponent. Minus just comes along for the ride. Negative 1/2 plus 1 would be positive 1/2 dividing by the new exponent, evaluated from 1 to 9. Now, how do you divide by a fraction? Keep, change, flip. That will be 2/3. I'm going to go ahead and plug in the 9 to both of these. So 9 to the 3/2 power minus, keep, change, flip here. This will be 2. Oops. 9 to the 1/2 power minus, and in parentheses, same thing, 2/3. 1 to any power is just 1. 1 square root of 1 is just 1. We get a minus 2. All right, what is 9 to the 3/2 power? That means take the square root. Square root of 9 is 3. Cubed is 27. So 9 to the 3/2 power is 27, but that's going to cancel with this 3, leaving behind 9 times 2 is 18. So I'm just out of space here. I did a bunch of arithmetic right there. Same game here. 9 to the 1/2 power is 3 times 2. That'll be minus 6. Minus 2/3 minus 2, that'll be 2/3 minus 6/3. So that this whole thing is negative 4/3. So I'll have minus, minus, I'll have plus 4/3. So that's 16 plus 4/3. Let's see, 16. Remember, I can do all this in my calculator too. So just to do that, 16 plus 4/3. And then if I want to turn that back into a fraction, I can hit math. I want into fraction, so I hit enter, and then I hit enter again, 52/3. That's my final answer. And I could have done that right here if I didn't want to do all this by hand. 2/3 times 9 raised to the 3/2 power. So in parentheses, 3 divided by 2. Minus, like I'll write it out, 2 times 9 raised to the 1/2. Minus, and then I want all this in parentheses, 2/3 minus 2. Oh, and I forgot my parentheses. Here we go. 2/3 minus 2. And let's hope I got the same answer. Let's check and see. If not, we'll find a mistake. Did I get some? Yeah, I did get something different. All right, let's find the mistake. Let me pause a second. I found the mistake. It was right here. That was this chunk right here was minus 2 times 3. That should have been a 6. So let's clean that up. So this was minus 6. And then that was plus 4/3. So that's 12 plus 4/3, which is 13 1/3. And then if I wanted to, again, I could change that into a fraction. 40/3 is the final answer. So when you're dealing with all these fractions, it's a good idea to get your calculator out, check all your arithmetic, make sure you didn't copy something down silly like that. All right, it's a good place to stop this one.